Hello, class. Today we are going to look at covalent molecules that display something called resonance. So the word resonance is actually something that comes from physics. When something resonates, they usually refer to waves that resonate between 2 points. One of the common things they may show you in a physics course is how a tuning fork has waves that resonate between the two ends of the tuning fork. And as a result, you hear a pitch. When we're talking about molecules in chemistry, resonance refers to a similar idea where electrons can kind of move between multiple atoms. They're referred to as delocalized. So let me add that to our notes here. Resonance refers to delocalized electrons. If something is localized, it stays in one spot, but when we have delocalized electrons, they have the ability to move throughout different areas of the molecule. And specifically, this refers to electrons that are shared between two atoms. They have the ability to move between the atoms that they're being shared with. This occurs when we are able to draw more than one valid Lewis structure for a molecule or an ion. We've seen some of these examples in the past as we went through the process of learning how to draw Lewis structures. As a result, no single Lewis structure can adequately describe the real molecule. The actual structure is a hybrid or a blend of all of the possible structures that we can draw. Now, this idea of electrons being delocalized actually can affect our bond length and therefore the bond strength. So in this particular example with ozone, we know that a single bond in ozone has a length of 147 picometers, and then a double bond has a length of 121 picometers. What happens with ozone is that we can draw two possible structures where that double bond is either on the right side of the molecule or that double bond is on the left side of the molecule. What's really happening here is that when we look at the structure of the molecule and take the orbitals that are available into account, we know that oxygen has both s orbitals and p orbitals. Now, a s orbital, if you remember, is spherically shaped, and a p orbital has this dumbbell shape. Now, when we're looking at a p orbital in a particular atom, we know that an atom has 3 p orbitals and 1 s orbital, and that makes up our 8 valence electrons, right? Because you can have 2 electrons in each orbital, and that gives us our 8. When we're actually drawing these, the orbitals, if we look at an x, y, and then z axis going out of the plane of the paper, the p orbitals form this really unique shape. We know we have one that's in the x-axis, one that's in the plane of the y-axis, and then we have a third one that's going out of the plane of the paper away from us and then coming towards us. Now, some of these orbitals are going to be occupied by lone pair electrons, and then some of them are available to bond. When we have molecules with resonance, what ends up happening is that you get extra p orbitals that stick straight up in the plane of our molecule. As a result, if you're looking at the molecule, you have this area above and this area below where electrons can freely travel back and forth. They can travel between this part of the orbital, this part of the orbital, or even this part of the orbital and this part of the orbital. I know this looks a little muddled when I go to draw it, but as a result of these p orbitals that allow electrons to freely move, we end up with delocalization. So because we have orbitals that are available up here for electrons to move, we end up having regions where these electrons can kind of float back and forth. As a result, they're actually equally shared across the entire molecule. So the structure on the left shows that double bond on the right, but in reality, that double bond is not on the right. It's also not on the left. It's somewhere in between. What this refers to is a partial bond character. So the real bond of this molecule is somewhere between the 121 picometers of a double bond and the 147 picometers of a single bond. So the real length is 128. What this tells us in this particular example is that the double bond, the electrons that are part of that double bond, are actually equally shared across the whole molecule, and we see this dashed line notation, which refers to that partial bond character. When we talk about bond orders in an AP chemistry course, there's a way to quantify how much of a bond belongs to a certain atom. But in this case, we just need to know that when we go to draw these molecules, that there are multiple ways to represent them. What's interesting is because the actual length of the bond is 128 picometers, both of these bonds are actually the same length. That is a unique thing about resonance. You would expect, based off of what you would draw, that this would be longer, this would be shorter because of how we drew them. But because those double bonded electrons are actually shared across the whole molecule, we end up with the same length for our bond. And since we end up with the same length, that also means same strength. We know typically that a double bond is stronger than a triple bond, a double bond is stronger than a single bond, and then a triple bond is stronger than a double bond. When we get into molecules with resonance and hybridization, you actually end up with somewhere in between. So to show this, we're actually going to draw the oxalate ion. In the oxalate ion, I know I've got 6 electrons for my oxygen times 4 gives us 24 electrons total. My carbon, I've got 4 valence electrons times 2, that's 8 electrons total, plus 2 electrons from my charge. In total, this gives me 34 electrons to work with. When I go to draw this, I have to keep that in mind. So I've got C, and then I've got an oxygen. I'll create my skeleton structure for each. And then I have to create my octet. So far I've used 10 electrons out of my 34, so I have 24 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now at this point, when I've drawn this, I have completed my octets for each of my oxygens, but carbon does not have an octet. So I know that I need to take a pair and make a double bond, and that satisfies the oxygen on the right. I do have to do the same thing with the oxygen on the left. This is one possible way to draw this structure, and the overall thing has a 2- charge. When we do resonance, we use this double-sided arrow to represent equivalent structures. I did not have to take the electrons on the bottom oxygens to make my double bond. I could have taken them from the top. So a different structure I could have drawn would have been this one. This is also a valid Lewis structure. I could have even drawn a third one if I wanted to. I'll get outside of the box here, where the double bond is up top on one of them, but down below on the other. As a result, what happens is that we see that these electrons that are part of this double bond resonate or can move back and forth between each of the carbon-oxygen bonds. So they are considered to be delocalized, the electrons that are part of the double bond. If I were to check the formal charges on these, my carbons each have a 0 formal charge. The oxygens that have a double bond also have a 0 formal charge, and I end up with a -1 formal charge on each of these singly bonded oxygens. And since we add up our formal charges to get the overall charge, we do end up with a -2 charge overall. When we do this in practice, I would start by drawing one of your structures. The best thing to do after that is draw it the exact same skeletal configuration. Don't try to move atoms around. Draw it exactly the same as you did before. Just move the double bond between the atom it was with previously and then the atom immediately adjacent. So you'll see that this can move to here, and then vice versa, this can move to here, but this cannot move to here. That's not how that works. It has to be an adjacent atom that it moves between. When we see this keyword all, that is usually a big sign in the problem that you have resonance that will occur and you need to draw more than one structure. Some of them you'll have to only draw 2 structures for, but others you could have to draw up to 3 or 4, just depending on how many possible ways that double bond can be moved across the molecule. That is all for today.